Okay, so welcome everyone to another talk in the Northwest Database Society series of talks. Today it's my great pleasure to introduce Bailu Ding, and Bailu is a researcher at Microsoft Research. Bailu got her PhD from Cornell University with Johannes Kerke, and actually before she graduated, she spent 3 years here at UW in this group from 2013 to 2016. And then she joined Microsoft Research, where she works on various aspects of query optimization and their interaction with machine learning. She's also the author of the recent super important survey or book, I should say, on extensible query optimization. And we are so lucky that she is here today to give a talk on exactly this topic. So Bailu, take it from there.
Yeah. Thanks, Dan, for the nice introduction. So I'm very happy to be back at UW to talk about the extensible query optimizer in practice. So I'm a researcher in the data systems group at Microsoft Research Redmond Lab. I think I have met many of you in the past meetings before, so it's great to see you here. Okay, so as Dan mentioned, we had a recent book on query optimization where we cover a bunch of different topics about like the basics of query optimization, the extensible query optimizer with a focus on Volcano Cascades framework, as well as other topics such as important transformation rules, cost estimation, a bit about how to manage the life cycle of query plans, as well as some of the open challenges in this field. Now, for the sake of this talk, I'm just going to give a high-level overview of the basics of query optimization and how Volcano Cascades works as an extensible query optimizer. Now, let's get started with some background. So there are many components in the process of processing a query. So the input of a query is just a SQL query, where you take the query and then you pass the query into our abstract syntax tree, where you do some validation to ensure the query is correct and satisfies the grammar. And then this abstract syntax tree will go through the query optimization to produce a physical plan to actually like about the physical operators and how to access the data. With this plan, it will go through the query execution engine, which will actually process the data and generate the query result. So in this stack of query processing, the role of the query optimization is just to take a logical query plan or abstract syntax tree and try to find a physical plan of the cheapest cost. Now, these why we need to find a plan of cheapest cost, because there are many options for the physical plans to sort of execute this query. So where do these options come from? So there are logical plans that are equivalent to other logical plans with some of these logical equivalents. One example is that we have join commutativity. Now, the join of R join, the result of S join T, if it's in your join, is kind of equivalent to switch the order of R and the result of S join T. Now, in addition to this logical equivalence, for every logical operator, we also have different choices of how to implement this logical operator. Now, for example, for a join operator, we have like hash join, nested loop join, merge join, or other types of different join operators. So there is a choice of this join operator. Of course, in addition to like figure out what are the alternative physical plans for the logical plan, we also need to compare the quantity of these plans. This is usually sort of measured by the cost modeling in the database system, which considers, for example, the cardinality estimation of the operator, as well as some of the cost function to understand, compare the different physical implementation of the operators. Now, for the sake of this talk, I will be mostly focusing on the search part of the query optimization. Of course, the book itself will cover additional topics about cost modeling, and cardinality estimation and cost functions are indeed have a rich body of literature. They are also active area of research now as well. Okay, about the search of the query optimization, let's warm up with just a join order enumeration. So the problem is to find the best join order for a select project join queries with linear plans. So linear plans is basically you join one relation after another relation after another relation. So this is also like the left dip or right dip trees. Now for this particular problem, even if we just go to this sub-problem and we try to enumerate different join orders to find the best order, if we just do a naive enumeration, the complexity is the factorial of n, which because we need to enumerate every permutation of the relations. Now, the pioneer in query optimization, the system R, actually proposed some more efficient joint order enumeration algorithm to address this problem. The key insight they have in system R is that in order to get the optimal plan for joining n relations, we can just extend the optimal plan to join n-1 relations with an additional relation and with an appropriate choice of physical operator of the join operator between those two. Now, here's a simple example of join the relations R, S, and T. We start with the best way to access the relation R, S, and T. And next, we move on to consider the best plan for join two relations, which can consist of the best plan we already found with one relation. Now we move to the join of three relations, which consists of different options to have two relations and join with one more relation. And of course, we also consider the cost of the physical operator to perform the join of the three relations. Now, this is actually the bottom-up dynamic programming based join order enumeration, and the complexity is actually reduced from the factorial of n to the n multiplied by 2 to the n. So this is a huge reduction in terms of complexity. Now, the other important concept proposed by system R is the interesting orders. So if we look at this example, we just join two relations with a merge join and a hash join. Now, the hash join is much cheaper because mostly because the sort operators for the merge join is very expensive. Now, assume for a moment if we have appropriate index that is available for way to access the two relations with a certain sort order. So basically, when we read the data from the index scan on R and S, they are already sorted by the join column. Then the merge join becomes much cheaper because we don't need the actual expensive joins. So basically, what this example shows is that the sort order of the relations can make a big difference in the cost of the plan. So we would like to incorporate this aspect into the join order enumeration. Now, what we're doing here is that in addition to find the optimal plan for joining n relations, we consider the combination of join n relations plus the output is in a specific interesting order. So now we, in addition to find the best plan to access the relation R, we also find the best plan to access the relation R where the output is sorted by, for example, the column A. Now with this, we again can go back to the subproblem decomposition to sort of incrementally build up the best plan for each of these individual expressions we are interested in, and the sort operators can be added in this process if the interesting order that is desirable is not provided by the underlying relations. Okay, so far we're all good with join order enumeration with SPJ queries. Unfortunately, in 90s, 80s and 90s, the field of analytical queries becomes so popular, and the requirement for like different features to analyze data also become more rich. Now, for example, there are additional new transformation rules in addition to like join commutativity and join associativity. People have discovered in some cases you can push down a group by below a join, which can significantly reduce the cost of the plan in some cases. Now, there are also new operators that is incorporated in the data analytics, such as the outer join operators. Now, instead of unlike the inner join operators, which can commute with each other, the outer join in general they don't commute with each other. So there are these or new constructs in the analytical database engines. However, for system R, well, every time you have this new transformation, you have this new operators, you need to rethink how to do the subproblem decomposition, because now it's not just extending one relation with another. You need to consider like which part needs to contain this group by operator and which relations can commute with themselves if in the presence of outer join. So this is not like undoable, but it's just difficult to manage and maintain the search algorithm with increasingly number of new rules and operators. Now, at that time, because of this kind of challenge in the system R's join order enumeration algorithm, there is a lot of work about how to incorporate new rules, design our extensible query optimizer where you can incorporate new rules and operators without requiring significant changes to the search algorithm itself. Now, along this line of thought, there is a lot of work about abstract the query optimization to an extensible framework with a rule-based transformation. For example, the Volcano and Cascades framework are along this line of thought. We also, over the years, we observed there are like a lot of industry adoptions for this kind of framework, like Microsoft SQL Server and Orca, which is the optimizer for Green Plum, and also Cascade. Of course, there are other examples of extensible query optimizers such as Starburst and Catalyst. They are designed in a different architecture, which I will not cover in this talk.
Short
Yeah.
interruption. Can we remove the OK? Okay.
Let me see. How should I?
Do you have it OK on screen?
No, I don't.
Yeah, okay, so then you need to find the mouse that goes to this OK.
Move the cursor. Thing on the right, just look for it. There's a filter.
Move the cursor.
On the right of that bar.
Oh, no, I see it.
On the right of that bar.
And we can back this one. Okay.
Okay, thank you so much. Okay, so before diving into the Volcano Cascades framework, let's first understand what are the rules, because this is a very important concept in the rule-based transformation, rule-based transformations. Now, okay, no, I think it's not moving.
Okay.
Okay, good. Yeah, now it works.
Oh, okay.
Okay, sounds good. Okay, so the rules is an abstraction which just transform an expression to an equivalent expression. So the expression can be either logical expression or physical expression. Now, what are some examples of the transformation rules? Now, one kind of rules is called transformation rules, which is just to transform a logical expression to another equivalent logical expression, like the joint commutativity in this case. The second class of rules is the implementation rules, which tries to transform a logical operator into a physical operator. Now, there can be different choices of physical operator. Now, in this particular example, we're just transforming the join into a hash join. Now, there are a third class of rules, which is called enforcer rules. Now, these rules, they doesn't change the equivalence of the expression, but they change the physical properties of the output of the expression. Now, one example is the interesting orders we just saw, which is sort order of the output. And in general, there are other concepts like the degree of parallelism of this operator, whether it's single-threaded or multi-threaded. So these are all kind of can be changed. These are all physical properties that can be changed with the enforcer rules. Now, with these rules, how can it support new transformations? Now, for example, if we want to add a new rule to do the goodbye push down, what it requires is that we need to add a piece of code to detect when this rule can be fired and to implement what is the transformation of this expression after the rule applies. So in this example, we just detect, okay, there's a goodbye over a join, and under certain, if certain condition has been satisfied, this goodbye I can push down to the right child of the join. So in this case, a new transformation is supported by adding a new rule. Okay, so with these rules, how do we explore all the equivalent expressions? Now, if we start with this join of RNAs, with the three classes of rules, we are going to derive a different kind of expressions that is equivalent to this expression. And in addition to that, after, for example, for the hash join, we can further decompose the base plan for the hash join of RNAs as the root physical operator plus the base plan of the child expressions. So in that case, we are doing the same subproblem decomposition, very similar to the concept of what System R is doing for join order enumeration. And we can also use the dynamic programming in this case. Okay, now we go through an example to show how the search in Volcano actually works. Now, this is a top-down search based on dynamic programming. And we start with the original expression, like the root expression, which is the R join S in this case. Now we can transform the join into a hash join with an implementation rule. Because we know the cardinality of the child expressions, we can cost the hash join operator itself with a cost of 180. Now, after that, we do the subproblem decomposition, and we recursively sort of derive the base plan for accessing the relation R and accessing the relation S. Now, after that, when we go back to the hash join of INS, now we know the cost of this plan is 290. Now, in addition to the implementation rule, we can also apply joint commutativity to this expression, where we transform that into the S join with R. Now, again, we can follow by implementation rule, which changes the R join, transform the join into a hash join. So at this time, because the root operator itself, the hash join itself, already cost higher than the base plan so far we have found, there is basically no need to continue the transformation. So we just can skip the further exploration on this path. Now, from the join of S and R, alternatively, we can, of course, apply join commutativity, but this is we have already started with this R join S. So this is a kind of a duplicate derivation. We can also stop there. So with this query, now we have the base plan that cost 290, which is the hash join between a table scan of R and table scan of S. Now, as you can see, throughout this process, we need to keep track what are the expressions we have derived, and we need to keep track what are the base plan for those different expressions. Now, in order, yes.
Is it volcano because it's from the top down?
That might be a possibility. Yeah. Okay. So in order to keep track of all the expressions we have derived in a kind of efficient way, so there is a data structure memo that is proposed to kind of keep track of the expressions during the search so that we know what we have derived so that we don't do duplicate work. And also because we want to manage the memory space, the storage space of the expressions, the memo is designed to be a compact representation to cache all the expressions. So the first concept in the memo is called a group. So basically it represents our equivalent class of expressions. Now, given these R join A's, there are actually three groups. The first group just represents every expression that is equivalent to R join A's. And the second group is just for everything equivalent to R. And third group, everything equivalent to A's. Now, the second concept in the memo is called expressions. So this can be either a logical expression or a physical expression at the root, the operator at the root. And the child expressions, instead of having the complex expressions, it actually has a pointer to the groups. Because, for example, in this case, we have the R join S. In this case, the child expression, instead of using R, we're pointing to the group that contain all the expressions that are equivalent to R. Now, similar for the group 3, which is all the groups that are equivalent to S. Now, in addition to the logical expression, we can also have the physical expression where the join is between the hash join between the two groups. So both of them are called expressions in the memo. Now we walk through the continuing example to see how the memo is used to cache the derived expressions. Now here we continue the same search process as before. We go to R, derive the table scan of R. Now during this process, we continue to fill up the memo with all the expressions. Now we have the join of S and R, and then become the hash join of S and R. Now from previous example, we know like we're not going to continue the exploration on this expression because it's too expensive. But assume for a moment, we don't have, this is not a point by the cost. If we want to continue the exploration of S hash join R, what will happen is that when we try to find the best plan for S, we know we have already derived that for S in the previous exploration. So instead of continue this exploration, we just can use the cached best plan for S. Now this is the same for R because we already finished the exploration, derived the best plan on R. We can just reuse the result. Now finally, remember the case where we want to apply again the join commutativity to S join R. With a memo, we can also detect this expression has already been derived before, so there is no reason to continue the derivation. So the memo structure is actually kind of very useful it's actually the data structure for the dynamic program. Yeah. So far, so good. Okay.
Also,
yeah.
because you're getting pretty quickly, so let's just make sure that people have time to like adjust the slides, right? And
Sure.
Just want to make sure people who are familiar with egg, they will recognize the memo as being an E-class. Yeah, it's a project that goes.
Okay. Cool.
of course, Volcano being much older.
Yep.
In the 90s, yeah. Okay, sounds good. So after getting the key concepts in Volcano and Memo, so let's take a look at how to support a new transformation in Volcano, like with the previous example of the group by pushdown. So assume right now we don't have this new transformation rule. What we are going to do is that we're going to do an implementation rule to convert the hash, the goodbye into, for example, hash aggregate. And then we're going to do the recursively find the best plan of the join of R and A's, just as you see in the previous slides. We'll continue this search. Now, assume for now we have a new fancy rule which can push down the goodbye operator below the join. With the new rule, we simply transform the expression into our new expression after applying the new rule. And the rest of the search will continue just as before, where you can apply the implementation rule you already have in the system. You can decompose the problem by doing recursive search to eventually find the best plan for this expression. So as you can see, in our Volcano-based query optimization framework, it doesn't require the change to the search algorithm itself in order to support a new transformation rule. So this is where the extensibility comes from. Yeah. Okay. Now, so far I just give you a mental picture of how Volcano works. But in reality, the implementation of Volcano is slightly different. So it actually separates the search into two phases. There is a generation phase, which do a top-down search to generate all the alternative logical expressions. And then it does a cost analysis phase, which is also a top-down search, but to find the best physical plan of the subplans. So as you can see, also our mental picture is like a top-down search, one-pass top-down search. In Volcano, it's actually a two-phase separation between the generation of logical expressions and the physical plans. Now, of course, if the search is kind of exhaustive, which means we will explore every combination of logical and physical plans, this is fine because we are eventually going to explore the full search space. However, in reality, especially in production and database systems, the optimizer usually just have a time budget to come up with a good enough plan for the query. Now, when the query is very complicated, like many joins, usually there will be a timeout for the search process, and the search is unfortunately not exhaustive. So what will happen with this two-phase separation is that we'll spend a lot of time to generate all the alternative equivalent logical expressions in the first phase before we get to any physical plan in the second phase. And what is worse is that for all the logical expressions generated in the first phase, some of them are not even used in the second phase because the search has been timed out before reaching like the physical plan for this. Yeah.
Just a quick question. Maybe I missed this part, but why did it start with a two-phase derivation implementation in the beginning?
Yeah. This is a good question. I also would like to know the answer. But I feel this is maybe your design choices of Volcano. And I think one benefit, this is just my hypothesis. I think one benefit is it has a clear separation of logical equivalence and physical equivalence. Maybe conceptually it's simpler, but I'm not entirely sure what are the rationales of doing this two-phase separation. Yep.
So this was Volcano in the early 90s, late 80s, early 90s, from this concept. This was Gus Griffiths.
Yeah.
Yeah, so this was immediately superseded by Cascades.
Yes.
Pretty quickly.
Yes. Someone from the online?
Yeah, can I ask a question from online?
Yeah, we can hear you.
Yeah.
Hi, just also saying hi to the group. It's Remy here speaking. Yeah, so my question is, so before you showed us that during exploration, when you realize the cost is exceeding kind of your current stat cost, you will stop, you will prune, right? But if you separate this into two phases, then how do you know when to prune or not?
Right. So in the first phase, in the logical generation, there is no pruning because there is no cost. The cost-based pruning only happens for the second phase when you actually derive the physical implementation rules.
I see, thank you. And this is in Volcano, but is this also the same in the Cascades? It's not here.
To some extent, it's the same concept.
Oh, it is.
Because the cost is only derived for physical operators, not in the original framework. It's only derived for physical operators, but of course, now you also can have some estimate of the cost even if you don't have the physical operators. So that's beyond the scope of this talk. But for the original Volcano and Cascade, you only derive the cost with physical operators.
I see. Thank you.
Yeah. Cool. Okay. in addition to this two-phase derivation, one other sort of a property of the search strategy in Volcano is that it kind of, because it uses the recursive depth first search, you kind of drill down very deeply into find the best plan for one child expression before you're going to derive any physical plan for the other child expression. This is just a property of the recursive depth first search. Now, in this case, to some extent, what will happen is that you are kind of explore the search space a little bit like region by region. Now, again, this is benign if there is no, for example, if the search is exhaustive. But again, when the search is not exhaustive and you explore the search space region by region, you may miss out some of the more promising regions if the search times out. So these are some of the properties of the search strategy in Volcano. Now, as Dan mentioned, very quickly, Cascades was proposed and become a successor of Volcano. So there are a lot of similarities between the two frameworks. The Cascades is also based on the idea of top-down search with memorization based on dynamic programming. They have the same rule-based transformations. They have memo, they have group, and expression. So all those concepts are very similar in those two systems. But based on the search strategy of Volcano, especially when the search is not exhaustive, the design goal of Cascades is to change this like two-phase monolithic search strategy into a more incremental search strategy where you can interleave the derivation of logical and physical expressions. Now, the key intuition of how to doing this interleaving is breaking down the search process into a fine-grained, smaller chunks of work, which they call the tasks. Now, we will have an overview of how the tasks look like in Cascades. Now, in the Volcano, we'll really see there are basically two big tasks. One is the generation phase that derive the equivalent logical expressions. The other one is the cause analysis phase, which find the best physical plans. Now, in Cascades, there are four tasks, sort of kind of similar to the concept of those two. Now, there is the optimized group, which tries to return the best plan for the group of expressions. There is the optimized expression, which returns the best plan, best physical plan for this expression. Now, the explore group tries to generate alternative logical expressions for the group, and the explore expression trying to go from like derive new expressions from this expression. Now, in addition to these four tasks, there are two additional tasks, which is called apply rule and optimize inputs. So what apply rule tries to do is that when I say I want to apply, for example, when I want to optimize the expression by applying an implementation rule, instead of performing the implementation right away, we just schedule a task to apply the implementation rule. Now, this is called apply rule task. Similarly, if we do apply a transformation rule to generate an alternative logical expression, this is also scheduled as an apply rule task instead of doing the transformation right away. Now, the other special task is called optimize inputs. So basically, this tries to kind of add some control flow based on the dependency of the tasks, because with dynamic programming, we need to like first derive the best plan for the children before derive the best plan for the parent expression. So this optimize inputs, you try to add some control flow because the whole task, iterative task scheduling is using a stack. Okay, we're going to show our example to walk through like how this task works and interact with each other. Now we started with the same example of R join S. Now I have pre-populated the groups in the memo to visualize how the memo get filled up during the search. Now on the right side, we'll show the stack of the task as they sort of pushed into a stack and pop out of the stack. When we get started, we'll add a task to just optimize the group of R join S. Now, because when it's added, we haven't explored any logical equivalent expression for this group. So we will add a task to explore this group to populate the logical expressions. Now, at the explore group, what it simply does is just a wrapper to sort of explore all the expressions so far we have derived in this group. So you will add an explore expression task. Now, next, because we are exploring this expression, we are doing actually two things. The first thing is that we are generating the applying logical transformations to this expression. Like for example, we can apply the join commutativity to this expression, and we added the apply rule task for that. In addition, we're also going to issue some task to explore the group of the child expressions. In this case, we're going to explore the group of A's and the group of R. Now, right now, we're at the end of the step, which is the explore the group of A's. Now, again, because we're going to back to the explore group task, we're going to explore the expression of A's. Now we're going to explore, because there is no other transformation rules, like logical transformation rules can apply to this expression. The stack will just backtrack because we are done with this. And with the explore group, we are also done with this. Now we backtrack to the explore the group R. Again, we're going to explore the expression in the group of R, and then we backtrack, and then we come to the point where we want to apply the joint commutativity to the expression of R join S. Now, in this case, what will happen is that after applying this joint commutativity, we'll get a new expression, which is the S join with R. Because this is a new expression, will in the apply rule, will actually issue the explore of this new logical expression. Because we have a new logical expression, we want to, again, try to see if there are other logical transformation rules that can be applied to this new logical expression. Now, in this case, we'll see like we go back to the explore expression. We'll spawn like 3 different tasks. The first one is that we apply the joint commutativity, and the second two is that we are going to sort of explore the group of its child. Now, at this point, because we look at the memo, we have already done the explore group of S, we have already done the explore group of R, so we're going to backtrack and pop them out. There is nothing else we need to do. Now, with the apply rule of joint community, we're going to go back to the expression of R join S, because it's a duplicated thing based on the memo. Well, there is also no need to spawn any additional task, so we're going to backtrack again as well. Now, here, after we sort of finish these tasks, the exploring the expression of S join R also finishes, so we'll backtrack. Now we'll continue to backtrack because this has finished, and we have populated all the groups for R join S. This also has finished. So we're now backtrack to the root, where we just try to, our goal is to optimize the group of R join S. Now at this point, because we already explored this group, we're going to optimize the expression. I'm so sorry. Yeah, we're going to let me double check. Yeah, because we're going to optimize this group. We're going to optimize the expression of R join S and S join R, because we're going through all the expressions in this group we have derived so far. We're going to schedule 2 tasks to optimize the expression, which is optimize S join R and optimize the expression of R join S. Now at the top of the stack, now we're optimize S join R, we can apply implementation rule to transform the join to the hash join. Now with that, we're going to again go into the apply rule expression. Now we go to the apply rule, we actually do the transformation of apply the transformation of converting the join into a hash join. Now we're going to go to the recursive part or go to the sub-problem decomposition part. We're going to schedule the task to optimize the inputs of the A's hash join with R. Now in this case, we first start with the optimize the inputs, the A's, the first input of this expression, which will goes back to get the best plan for this group. Now with this task, we're going to continue to optimize the expression of A's, which just have a single expression in the group. So we just optimize the single expression A's and go through the application rule implementation rule of turning the A's to a table scale A's, apply the rule. And because this is just a leave operator, there's no inputs that is left for optimize this. So we'll backtrack because we're done. We'll backtrack and because we're done with optimizing the group or the group for S, we'll backtrack again. Now at this moment, we're done with optimizing A's in A's hash join R. We are moving to the second input, which is R. Now we're going to optimize R. The process is actually pretty much this. We get the best plan for R, get the optimize the expression for R, and resulting in a table scale of R. And at that point, we're going to backtrack again and again. And then because now we're done with optimizing the expression of A's join R, we'll backtrack again, and we'll continue to optimize the best expression for R join S. So the process is very similar to the previous one. And just in some cases, because we are optimizing, when we're optimizing the R and S, in this case, because we already know what is the best plan, we'll just reuse what has been cached in the data structure without doing duplicate derivation. Okay, so as you can see, the whole workflow of Cascades is very complicated, kind of much more complicated conceptually compared to the Volcano. So why are we doing all this? Now, the first benefit is that, see, the apply rule task actually can be scheduled by both logical transformation and physical transformation. So in principle, if we look at some of the complicated queries, we could observe that the derivation of logical expressions and physical expressions are interleaved with each other. Now, unfortunately, this is not demonstrated in the example previously because we need a bigger example to demonstrate the interleaving of logical and physical transformations, which you can find in the book. In the book, we have a bigger example of three-way join. Now, the second benefit is that if we look at how the tasks are created, now for the example, when we try to explore the expression of R join S, we are creating three additional tasks, which is explore the group of S, explore the group R, and apply the join commutativity. Now, these three classes, three tasks, actually has no dependency between each other at this moment. So we can actually parallelize exploration of these tasks. So this will help you to have a way to sort of do parallel query optimization. This is useful when the query is very complicated, and you can, by doing parallelization, you can reduce the time to spend on query optimization. In fact, OCAR is one of the Volcano Cascades-based query optimization framework actually have implemented the parallel query optimization. Okay, is someone online was speaking? Okay. Okay. So
Who are you talking to?
is someone talking online?
I don't think so.
Is there a question?
Okay, sounds good. Okay, so that's the how Volcano and Cascades works. So far, so good. Any question? I think it's a good time to check. Yeah.
Yeah, I'm just wondering, in a production setting, you might hit the timeout at, any stage and you
Yeah.
partially explore
Yeah,
one of
yeah,
these
yeah.
tasks. What do you do?
It's just timeout. And you timeout, and based on after your timeout, because the memo stores all the base plan you have derived so far, you will just construct the final plan, the base plan you can get so far from the memo. You just construct it. Yeah.
Okay, so this process you can interrupt. It's at any time.
Yeah, anytime algorithm. Yeah, exactly.
Yeah, so I
Any
have
other-
a question related to my last question. So now we're in this, mutually recursive functions, and then now we're actually optimizing. So now when does cost estimation happen, and then are there better opportunities for pruning in this architecture?
Yeah, that's a good question. So, for the sake of to have a manageable visualization, I ignored all the cost estimation process. But during all those tasks, now when the cost estimation is done whenever you get some updated on the physical plans derived through the process. For example, in the apply rule, so in each of the tasks, it actually come with a cost limit. Now you start with an infinite cost limit, and you keep updating the cost limit for each of the expression along the way. Now, one place to update the cost limit is when you apply a implementation rule. At that point, you know the physical operator of the root of the expression, and you can cast the root expression, and then the cost limit for the child expression will be updated accordingly. Now, the other part where cost is derived is the optimized inputs. So whenever you return from the optimized inputs, you know what is the best plan for one child, for the input you have derived. So at that time, you can also update the cost limit for deriving the later child, the next child, because now you have a exact cost for the previous child input. Does that make sense?
I see. Yeah. So basically, the green boxes before never was any costing. And then the red ones do costing, and I guess the yellow optimize, they will also replace the group cost with the best cost in the group. Right?
Exactly, along the way. Yeah. Now, a caveat is that there are some heuristics used for the explore group and explore expression as well, where you can derive or estimate some upper bound or lower bound of how the cost is going to be. Now, these are kind of estimates. You can incorporate that during the process, but the original Cascades does not assume you are doing these cost update for the exploration tasks.
Right, thanks.
Okay. Any other question? Okay. With that, I'm going to move on to give a few more examples of how the extensibility can be exercised in a sort of interesting way for Volcano and Cascade. Now, one example, we have already covered the example of adding a new transformation rule. Now, what if we want to add new operators? For example, the outer join operator, we add the logical operator, we add the transformation rule, and of course, we need to update the cost model. And of course, there are other additional rules that can be handled for outer join. But again, the search algorithm doesn't need to change. Now, finally, I just give another example of an interesting use of the physical properties. This is to extend the query optimizer to support distributed query processing. Now, when the data becomes large, sometimes you need to partition the data into different nodes for processing. But in some cases, the data need to distribute in a certain way to ensure the result is correct. For example, if you have a hash join and you are partitioning the data into two parts, you need to ensure both relation R and relation S are partitioned by kind of the same, to ensure the same join column will be located in the same node. Now, in the original query optimizer, the optimizer is not aware of all this, the partitioning or distribution of the data. So what you can do is that the optimizer can extend the physical properties to include how the data is distributed. Now, in this case, in addition to see the join of R and S, you are saying I join R, which needs to be partitioned on column A, and join S, which also needs to be partitioned on A. Now, if the partition is already available, then you can just directly access the data. However, if the partition is not available, for example, the S is partitioned round robin, there is no like distribution by hash function of the A star. Sorry, this is A star. Now, what will happen is that you can add a new enforcer to change the property of this partition. So in this case, it's shuffle operator. And then with the new enforcer, of course, you need to add new rules to sort of derive the enforcer during the search process. And of course, some costing of like how much cost it will take for the shuffle to do. But again, this doesn't need to change the search framework of Volcano or Cascade. Yes.
I'm just wondering about the name. What is it enforcing?
I'll just change the physical property. This is just, I think this term is proposed by Volcano framework. Yeah, the idea is to change the physical property.
It's annotating.
Yeah, to some extent, yes.
But also applying an operation that enforces that annotation, like
Yeah.
you're sorting, you're adding a sorting operator, and then it's sorted, or you're adding a shuffle operator, and then it is partitional.
Yeah. Yes.
So, something in a more distributed context, you have to take into account physical properties. You also have to take into account like which nodes would be participating in the query or things.
This is a good point. I think it depends how the system is implemented, but at the query compilation time or query optimization time, sometimes the database doesn't know like how many nodes it will get to schedule the query. So in this kind of system, the query optimizer doesn't know about how many nodes it will do. And the scheduling will only happen in query execution time. Yeah. Okay. We still have some time, so I'm going to move on to talk about some quote-unquote additional techniques to further control the search. All these techniques are mostly for database developers who want more control over like how to derive the search in the system. And I will be talking about two categories of techniques. One is how do we customize the search strategy. The other part is how to improve the efficiency of the search. Now, all these techniques has been implemented and used in some of the commercial database systems. Yes.
When you say database developers, does this mean Microsoft developers with a badge, or can this be any database?
Any database, yeah. Oh, no, you need to have, because this will need to change the source code. Unless the database have hooks for that. I think, for example, SQL Server, it actually provides some hooks to control the set of rules to use. So some of them are available, but I don't think everything is, yeah. In general, you want to have access to the code and you can change the database engine code. Yeah.
Is it possible to say, let the user extend the operator of the database? Say the user have their own operator over some piece of hardware, for example?
In general, I think, especially for the query optimizer, I'm not aware of any database that can support. You can implement that as kind of UDF, but I don't think in general the optimizer can be sort of changed if you don't have access to the code.
The most I'm familiar with is the user, for example, SQL Server can provide hints in the query that will change the strategy. But there's nothing that's like your own custom code, injecting your own custom code.
Right.
So in the compiler world, there's like XO compiler, which like let the user to decide like I can add this new operator to the compiler so that the user can use this kind of, for example, new piece of hardware.
Yeah, I think this is I'm not aware of any database system can do this. But you're right. There are many. I think Microsoft SQL Server, Oracle, maybe IBM, DB2, as well as Postgres, all provide query hints where you can use that to sort of change the behavior of the default query optimization. Yeah. Okay. Now let's start with the promise. So what the promise is trying to do is that, okay, in some cases, for a given expression, some rules are more likely to lead to a better plan compared to other rules. Now, assume in this case, we have R join S. If we know like the S is a smaller table, then it's probably more promising to do the join commutativity to put the smaller table on the build side instead of having a hash join of RS. So in these cases, we actually want to prioritize some of the transformation for an expression than others. So the promise is just kind of a concept which you assign a scorn to the pair of expression and the rule that is going to apply to the expression, so that when we're scheduling the task, we can sort of first explore the tasks that are more promising than the others. Yeah, then are you? Okay, good. So in general, if the search is exhaustive, the promise only changes the order we explore the search space. It doesn't change the query, like the resulting query plan. But of course, when the search is not exhaustive, it's always better to find a good plan earlier because it helps with the cost-based pruning. It also can improve the plan quantity if the search times out. Now, the other mechanism is a little bit different. It's called guidance. So the guidance, what it tries to do is that it tries to scope for example, you have a full search space, but with some empirical experience, you might understand, you might know like certain part of the search space does not make sense. So that you can supply some of the heuristics to say, okay, I don't want to explore this part of the search space. Now, one example is that, as we previously seen, it doesn't make sense to apply the joint commutativity twice. Now, instead of actually deriving the applying the joint commutativity twice and derive the expression is duplicate, we can simply deactivate joint commutativity if we know it's already applied once. So in this case, we're not really cutting the search space, but we're reducing the overhead of the duplicate derivation. Now I remember Sita has a paper about how to invoke all the sequence of rules, deactivating and activating the rules in a sequence so that you can explore the join ordering without deriving any duplicate. So there is one way to use the guidance. Now the other way that is also common is that just use the guidance to train the search space. One example, which is actually used a lot, I would say, in practice, is that in general, it's a good idea not to have cross product in the query plan. So the guidance can also use to sort of train this kind of stuff in search. Now, in addition to this customized search strategy, now there are other techniques which improve the efficiency of the search itself. Now, the first thing is the simplification rules. This is actually kind of important because you don't know how people write the query or how the queries are generated. Now, there are some cases where some rules are just always better to apply and lead to a better plan. Now, example is that remove duplicate predicates in your query, or we call this in some of the common expressions in the subquery to remove like part of the subquery. Now, instead of derive an alternative expression, it simply just replace the original expression with the transformed expression so that we can save a lot of derivation for the original expression. So this is one thing. Now, in general, the simplification rules can be invoked as a pre-processing step of the before like the actual query optimization to simplify the abstract syntax tree. But in some cases, you only find this opportunity of simplification during the search process after certain transformations. So the simplification rule can also be invoked during the query optimization process. Now, the other thing that is kind of interesting is that there are certain plan shapes we know that are kind of promising based on some heuristics. Now, one common example is that the star query or the snowflake queries, it's usually these queries is going to join a large fact table, which is zero large, and then going to join a fact table with a bunch of dimension tables. Now, it's a like heuristic, but it's actually a good idea to join the dimension table from the most selective to the least selective. Now, of course, with join commutativity and join associativity, we can like transform the query plan into this shape during the search process. But the issue is that if the original plan is in a very different like join order, it can take many steps to apply this commutativity and associativity rules in order to reach the desirable plan shape. Now, again, this is kind of benign if the search is exhaustive, but when the search is not exhaustive, sometimes you won't get to that desirable shape. Yeah.
One thing that's interesting is now that you start to add these extra rules like the heuristics and and there could be interesting like interdependencies. So like I'm a developer, right? I work on say the SQL Server team. I want to add some new rule. So before, like without the guidance, it's mostly systematic, right? I add a new rule that just expands the search space with additional operators or additional transformations. But now there could be some interactions, and then I could interact and have some bugs that maybe I added a new rule that causes something, and then the heuristic doesn't work. So what are your thoughts about those interactions?
Yeah. So I think especially for guidance, you need to be ended with care because you can trim the search space where you can miss out some part of the search space that may come with a good plan. So I think in general, I think especially for like commercial mature query optimizer, what people will do is that there will be a lot of testing and evaluation before these like change in the query optimizer go out. Yeah, because it also because the thing is that anything like especially the guidance etc. change in query optimizer can change the query plan. Now this can be a good or bad thing depending on like whether the performance of the query improves or regresses. Yeah, exactly. Actually, I don't have time to get to that, but in the book we talk a lot about the life cycle of plan management, including how people deal with regressions. Yeah. Okay. Now let's go back to the macro rule. So what the high level idea is that instead of doing like these mini step transformations, we just do dramatically change the plan shape in one transformation. So in that case, what is beneficial is that we ensure the optimizer to explore these good plan shapes early in the search. And in addition, actually, these macro rules are usually applied, give a very high promise to apply. So they are applied at the early stage of the query optimization. So this is especially beneficial, of course, for cost-based pooling, but more important for non-exhaustive search because this can ensure the optimal at least look at those candidate plans early in search space before the search times out. Okay, a final thing that is very important in practice is the multi-stage query optimization. So the goal is that instead of like firing all the rules for every query, we want to incrementally increase the search space if the query needs such a like search space. Now, for example, if the query is just very simple, it's like a scan a table, lookup of a single table, then it probably doesn't need all this overhead of incurring the whole huge set of rules. And also, because this is because the search often times out, unfortunately, we want to sort of progressively improve the quantity of the plan with more complex rules over time, if the time permits. Now, in this case, we will have like multi-stage query optimization where the query optimizer or the search of the query optimizer will be invoked more than once. So each time it will given an increasing set of rules for the search to explore. Now, in that case, we sort of gradually increase the size of the search space. And this is often implemented with guidance as well. So we use guidance to specify the set of rules that are activated in the search. Now, the memo and the other data structure or caching is shared across those stages. So we ensure there's no duplicate work across different stages.
So the question is, approximately how many rules are on that SQL server today?
So I think I can say there are hundreds of rules.
100.
Yeah. Some of the rules are very this is specific. Like there are rules that doing very complex decorrelation of subqueries. There are rules that are kind of useful for example, for like parallel or distributed query processing. Yeah, these are all that. Yeah. Yes.
Actually, just about these multi-stage
Uh-huh.
optimization. Are you aware of any database system that in the downtime, when it has less, load, spends some of those idle cycles doing this? Or is this only done when you see a query again and you're going to spend that 1 second to?
Oh, okay. So this is an interesting question because okay, I think this is beyond the scope of the talk, but in general for like commercial databases, if you have a query template, for example, there is a choice of optimizing every instance of the query template versus optimize the query template once and reuse that plan for later invocation of the query instances. And there are work actually this is an active research field called parametric query optimization, where you try to understand how to what are the kind of query plans you want to sort of choose for those different instances and how to choose them at the runtime. Yeah, but this is actually not for query templates. So this is just for example, if you have an ad hoc query or the first time you optimize a query template, you will, depending on the complexity of the query, there can be different stages triggered for the query optimization.
Okay.
Yeah, and also in addition to that, there is a timeout. Even for the the stage where you have all the rules activated, there is still a timeout associated with that. So you won't doing query optimization forever for the query.
Gotcha. Okay. So this is not for recurring queries. This is one query that you have.
Yeah. Or the first time of the recurring queries when you get the first plan for that. Yeah.
Perfect. Gotcha. Thanks.
So maybe a follow-up question. Is it possible to say keep the memo table like always in the memory and I don't like recompute the memo table for each new query? But even if a query is new, like there may be some subpart that's shared with the old query. For example, the join between say the person and their occupation is very frequent.
I see. Yeah, I think this is the possible. But you need to have the same expression plus the same predictive values because if the predictive values are different, the cost estimation will be different, and the exploration of the search space will change. But I'm not aware if any of the query optimizers is doing this kind of caching.
I just think like the search space between different queries overlap a lot. So like
they can overlap. Yeah. For example, like in a star query or in some of the like TPCH kind of data warehouse benchmarks, usually you are drawing the fact table with a bunch of dimension tables. Yeah.
We have a few minutes.
Yeah, I think that's my last slide. Good. So in this talk, I covered the basics of query optimization, especially the important concept from System R. And also we give a high-level overview of how top-down search with memorization works for Volcano and Cascades. Then I give a few additional examples of how the extensibility can be exercised in this framework, and talk about some additional topics about how to control the search space. Now, of course, the query optimization is a huge topic. There are additional topics covered in the book. So if you're interested in understanding the internals of query optimizer, feel free to check out the book. Yeah. So with that, I think we are about the time. Maybe we can take one more question if there is any question.
What we need to do, we first stop the recording.